So, good morning, afternoon, or evening, everyone, and welcome to QuCS. I'm Michael Roberts. I will be moderating today's session. Just a couple of things to note. Today's session is being recorded. I would like you to all please keep your microphone muted while the speaker is presenting, and hold all questions until there is a Q&A at the end.
嗯
You can, of
团队
course,
的每个
feel
人是都有自己的能力的，大家
um,
一块儿，既然传这个局，是不是咱们就把这个牌打好？
I'd like to remind you to please keep your mics muted until the Q&A in the end. Ishi, can you please take care of that?
对呀，
Thank you. Anyway, please feel free to type in the chat, and I'll read the questions aloud, though, when we get towards the end, towards the Q&A. So for today, though, it is my pleasure to introduce our speaker, Dr. Chen Zhao. Dr. Chen Zhao he joins from the Eastern Institute of Technology, Ningbo, as an assistant professor in fall 2026. He was a senior research scientist at QEra Computing and completed a postdoctoral fellowship at Harvard University from 2022 to 2024. He earned his PhD in applied mathematics from the University of the Chinese Academy of Sciences in 2022. His research is focused on quantum error correction with a focus on practical implementations for near-term quantum devices. So everyone, please welcome me in joining Dr. Chen Zhao.
Thank you, Michael, for your introduction. So let me try to share my screen. Okay, can you see my screen?
Yes, I can.
Okay. Okay, I'm very happy to share about our recent result on quantum error correction. The title of today's talk is Towards Ultra-High Rate Quantum Error Correction with Reconfigurable Atom Arrays. And this is a joint work with researchers at QuEra, Harvard, and MIT. So to start with, I want to briefly mention the challenge for large-scale quantum computing. So nowadays, because of the advancements of quantum devices, we can now reach the physical error rate around 10 to the minus 2 to 10 to the minus 3, so-called the NISQ era, where we can demonstrate some quantum advantage experiments on nowadays quantum device. However, if you think about large quantum algorithms such as the Shor's factoring algorithm or quantum chemistry simulation algorithm, you might need the qubit error rate below 10 to the minus 9. So there's a huge gap between nowadays physical error rate and the target logical error rate for large-scale quantum algorithm. But fortunately, we have the theoretical tools called quantum error correction, which can bridge this gap using some theoretical advance. However, the quantum error correction is usually costly. For example, if we think about Shor's algorithm, and the state-of-the-art algorithm will use around 1,000 logical qubits to factor a integer of 2448-bit RSA integers. And if you compile this 1,000 logical qubits using quantum error correction code, for example, using the surface code, then you might get the number around 1 million physical qubit on a 2-degree using the protocol of the surface code. And for the surface code, usually we will use around hundreds or even thousands of physical qubit to encode one logical qubit. But recently, there are more advanced in quantum low density parity check code, which can reach higher rates. For example, the recent IBM BB code can encode tens of logical qubits using around 1,000 physical qubit. And more recently, we benchmarked the new quantum error correction code, which we call ultra high rate code, where we can encode around 500 logical qubit using only 1,000 physical qubit. Basically, you can encode two logical qubit two physical qubit per logical qubit on average. And today's talk, I want to introduce more details about our work on ultra high rate code. Firstly, I will briefly talk about what is the construction of and the major principle behind this construction of this class of quantum error correction code. Then I will talk about how to implement this family of codes in a hardware efficient way on neutral atom hardwares. And finally, we will also talk about the performance of this quantum error correction code family in terms of the practical setting under the practical noise model. So first of all, I want to talk about the quantum error correction in a more general picture. So basically, in quantum error correction, we will encode the quantum information into logical qubit. And the way we encode the quantum information in logical qubit is to introduce the redundancy into the system. And using the redundancy, the quantum information will be encoded into entangled global information so that the local error will be detected by measuring those redundancy. And the general way of constructing quantum error correction code is to use the stabilizer formalism, where the stabilizer adjusts those local redundancy so that we can use those by measuring those stabilizer, we can catch the error and we can know what error happened within the system so that we can correct those errors. And as a concrete example, actually, the classical error correction code is also a quantum error correction code, although there are some um, um, property that is not ideal. So, for example, we can always encode the classical information by repeatedly So, for example, we can always repeat the 0 and 1 by
Uh,
many copies.
Dr.
Here we
Dr.
use
Zhao, we
one.
lost your stream. Sorry to interrupt.
Oh,
I think
sorry.
you lost. I think we
Can
lost connection for a second. Can you reopen the PowerPoint, please, on Zoom?
yeah, sure. Let me reshare my screen.
Thank you.
Sorry about that. Okay, so one example is to use the repetition code to protect the errors from to protect the quantum information interrupt by the bit flip error. So, for example, we can always repeat the logical zero by encode it into many physical zeros. Here we use five physical zero to represent logical zero states and five physical ones to encode one logical one state. And if there's a bit flip error happened on the fourth qubit, then we can always detect it by measuring the stabilizer or the parity between the neighborhood qubit. For example, the first two qubits, the parity will be +1, and once we measure the parity between the third and fourth, the fourth and fifth qubits, the parity will be -1. And what we will do after detecting those stabilizer measurement result or so-called syndrome extraction, we will use a classical program to infer what error happened within the system. And in this case, we might expect the fourth qubit will be flipped. And after the decoding and error correction, the quantum information will be flipped back by applying the correction so that we can protect the error, protect the quantum information from error. However, this is a classical error correction code so that we can only detect the bit flip error. But in quantum world, we also have the phase flip arrow. So what should we do to protect the quantum information from both bit flip arrow and the phase flip arrow? In the previous construction, one intuition you can imagine is that we use two classical error correction code to construct a one quantum error correction code. For example, we can take the product of two repetition code from the classical world to construct a quantum code. For example, the surface code, the famous surface code example, can be regarded by taking the product of two repetition code, and then we can encode one logical qubit into a 2D grid. And the local degree of freedom will be used to encode the stabilizer so that we can detect the error from by measuring the stabilizer or signal extraction. And there are two stabilizers in the surface code. One is the X stabilizer, which will be used to detect the zero errors, and the other is the Z stabilizer, which we will use to detect the X error. And the global information will be encoded into a global operator, which will cross the whole system from one boundary to the other boundary, so that the local error will not flip all of the information. So we can always detect the local error. And the most important theorem from my understanding in quantum error correction is the threshold theorem, where we can suppress the logical error by increasing the code distance exponentially. So in the example of the surface code, if we increase the size of the surface code patch uh, by increasing the length of the path, then the logical error rate will be suppressed exponentially once the physical error rate is below the error threshold. And more recently, there are more theoretical advance in quantum low density parity check code. And in the previous surface code construction, all of the stabilizer are geometrically local, but it can be generalized by relaxing the requirement of geometrical locality. So the low density parity check code in the classical world is that we use some stabilizer or parity check to to detect the errors, but those parity check will be sparse, so that each parity check will only touch several number or a few number of physical qubits. And in the classical LDPC code, it has been widely used in, for example, the 5G or Wi-Fi protocols. And the encoding rate of the classical LDPC code is usually greater than one half, and sometimes can be uh, closely approached to one. And it has very powerful or efficient, fast belief propagation-based decoding algorithm, which guarantee the performance of the classical LDPC code. However, if we think about the construction of the quantum LDPC code, we have to handle two type of error, not just the bit flip error. We also have to handle the phase flip error. And the because of the two type of error handleness, as we mentioned in the previous slides, the conventional construction of the quantum LDPC code is usually taking the product of two classical LDPC code. So in the previous construction, the rate of the quantum LDPC code is usually below or around 10%. So a natural question is that can we do better? Can we reach higher encoding rates, such as the classical error correction code, which can reach the encoding rate above one half? The major challenge in constructing ultra high rate quantum LDPC code is that in the classical construction, the higher rates are usually obtained by deletion. Basically, if you think about the parity check matrix, we just delete some of the parity check matrix, and the deleted rows will become the new logical degree of freedom so that you can encode more information. However, in the quantum code, it doesn't work because we have to handle two type of the arrows by measuring the X and Z stabilizers. And if you think about the X stabilizer and you delete some X stabilizer, those X stabilizer will no longer be detected by any Z stabilizer, so that those X stabilizer will become directly the X logical degree of freedom, so that the distance will be upper bounded by the original X stabilizer, which is usually low weight because of the LDPC construction. So that is the major challenge we have to handle. So basically, to construct a good ultra high rate code, we have to firstly it has to be a quantum code which should satisfy the orthogonality of the CSS construction, and we cannot use the row deletion construction from the classic world directly. And recently, a paper by Kenta Kasai come up with some construction which is novel in the quantum world. So the Kasai code is still a two-block code. Basically, the X stabilizer can be represented by two block of submatrix A and B, and the Z stabilizer will be the B and A with transpose, so that this form of the parity check matrix will satisfy the CSS orthogonality construction. And the basically the classical is still an example of the two-block construction where each block has more structures as sub-blocks. And for example, the X stabilizer will be represented by 3 by 12 subblocks, and each subblock represents a affine permutation matrix. And one important property in the Kasai construction is that those affine permutation matrices are no longer abelian. And in the Kasai construction, it's still follow the classical row deletion method to increase the encoding rate. However, it's not from the row deletion directly from some quantum code, because the if you delete some rows in the quantum code, then those deleted rows will directly become logical. So basically, the construction is from deletion from some master matrix of or parent matrix of the Kasai code. So the parent matrix of the Kasai code for X and Z stabilizer will becomes 6 by 12 blocks, and the last three rows of the X and Z parent matrices will be deleted, and the remaining rows will be served as the X and Z stabilizers in the Kasai code. And there's another additional restriction in the deleted rows, so that the deleted rows will satisfy the non-orthogonality requirement, so that the deleted row will no longer be a trivial upper bound of the code distance itself. And those non-orthogonality construction will be satisfied by using the non-abelianness of the affine permutation matrix. So basically, we have two blocks of the parent matrices. The first three rows will be served as the parity check matrix or the stabilizer of the code. And those three rows will satisfy the orthogonality construction. And there are some elements of the submatrices which satisfy the non-orthogonality so that the deleted rows will no longer be a trivial upper bound of the distance. And in the original paper by Kasai, he found a code instance of 9200
Dr. Zhao, I believe we lost him again.
I think that was first ever. I think that was the first ever time we ever had this case that our presenter has dropped offline. But just give us a couple minutes. Oh, Dr.
sorry
Zhao's
about
back.
that. I think my network is not very stable. Let me try to share my screen again.
It's all right. You are good to go.
Okay. Sorry about that. So in the original Kasai construction, he found a code instance with 9200 physical qubit, but encode around 4600 logical qubit with code distance upper bounded by 32, and the degree of the data qubit weight is 6, and the check weight or stabilizer weight is 12. And in the code capacity simulation presented in the original paper, the logical error rate or frame block error rate at the 4% physical error rate setting is around 10 to the minus 8, which is very impressive at the first time when I read this paper. So a natural question to ask is that can we achieve a good performance at the block length relevant to early utility scale application? So we want to find some smaller instance which can still reach the requirements of the large scale quantum applications, and how to implement this code efficiently on hardware, and does this code work well under the circuit level noise for real-time error correction? So to answer these questions, I want to briefly introduce more details about our work. So firstly, I want to talk more about the hardware efficient realization in neutral atoms. So let me briefly introduce the features in neutral atom arrays or neutral atom hardware. So the qubit will be encoded into atomic system where basically we encode the 0 and 1 into different levels in Rydberg atoms. And we can operate those encoded quantum information by using the laser or pulse by interacting with the atom and the laser. And because of the recent development of the laser technology and the Reaper Atom platform, we can reach high fidelity and parallel gates in those platforms. And most important, the other most important features on this type of Reaper Atom platform is the flexibility of the connectivity. Basically, you can interact or entangle arbitrary pairs of atoms by atom shuttling. So you can move the atom and pair them together to reach the entanglement you want to reach. In principle, this type of the platform can support arbitrary connectivity, but not all of the connectivity or atom shuttling are efficient. For example, in our previous results on magic state distillation, we carefully designed the atom movement in on the hardware of Quera's machine, so that we barely we mostly optimize the atom movement by using the control parallelism and reconfigurability, so that the atom movement will be patterned by row and column movement in parallel. So arbitrary connectivity may not be hardware efficient. So in this type of in real readable atom array platform, we might prefer the translation or rescaling as 2D grids, and row and column do not cross each other while moving. And we need to consider how to utilize these properties in implementing the quantum error correction on hardware. But fortunately, quantum error correction code usually have more structures so that we can utilize. For example, the recent developed the BB code, as well as the QuCS code instance we found in our paper. For example, in the previous construction of the hypergraph product code, basically you can utilize the product structure of the classical code, so that the atom shuttling will be compiled as the row and column parallel atom movement patterns, so that they can be efficiently implemented on hardware. However, even though with the product structure, the scaling of the general hypergraph product code usually needs log L depths of the atom movement, which will take around 20 milliseconds under the assumption of the nowadays quantum hardwares. But it will be more challenging to implement the QuCS code, because the underhood algebraic structure of the QuCS code is the affine permutation, which we originally thought it might be challenging. However, by introducing more structure in the code, we found we can still implement it in a more efficient way. So to implement the code, we need to figure out how to lay out the qubits to implement the synchrony extraction circuit. And the requirement of the synchrony extraction is that we need to prepare some ancilla qubits and reorder the ancilla qubit to entangle the data qubit to extract the synchrony errors to detect the physical error within the system. And the pattern of the reordering is described by the affine permutation matrices. For example, here the F0, F1, F2 to F5, and G0 to G5 are affine permutation matrices. So basically, we need to implement or reorder the ancilla qubits as the pattern described by F0, then transfer to F1, and then F2, and etc. The core requirement will be characterized by the transition matrix described by the different affine permutation, the product of different affine permutation matrices. So if we can design some protocol to implement the layout or the atom shuttling for this transition, then we will implement this quantum error correction code efficiently on hardware. However, the general construction of the affine permutation will require log p depth reordering in terms of the transition matrix. But what we further found is that there are some additional structure we can utilize to simplify this log p depth circuit, which can in principle give you constant depth circuits in the QuCS construction. So the idea is to reorder the representation of the affine permutation. So basically, if you think about the affine permutation, the naive layout of the affine permutation is from 0 to p. And if you want to implement the affine permutation, you take the index and multiply by some number, and then you will shift the index um, um, according to the definition of the affine permutation. However, we don't want to implement that because that will require log depth atom movement. The alternative way we found is that we can lay out the qubit by repeatedly apply the affine permutation itself. So the qubit will be laid out by the orbit of the affine permutation, so that the reordering of the affine permutation will be simply characterize the cyclic reordering, and there might be a lot different orbits on the affine permutation forming different rows. And by applying the affine permutation, you just need to shift the qubit according to the orbit. Basically, on a 2D grid, it will be a simple x direction shift. And the other question we have to answer is that how to implement the transition between one affine permutation to another affine permutation. To address this issue, we made an additional assumption by assuming there might be for other affine permutation matrices, those affine permutation matrices are commutative to the regarding to some reference affine permutation, so that because of the commuting structure of the affine permutation matrix we choose, they share the orbit structure of between different affine permutation, so that if you want to transfer from one affine permutation to another affine permutation, you basically need to reshuffle the orbits, then do some cyclic shift along these different orbits. And taking this requirement together, we choose the reference affine permutation first, then requires other affine permutations to be commutative respecting to the reference affine permutation. We set all of the requirements into the searching program in our code searching engine, and by running the searching iteratively around the server, we found several interesting code instances. Basically, at the smaller code lengths around 1,000 to 2,000 physical qubit, corresponding to 500 to 1,000 logical qubits. And the code instance we found in our paper is described by the table shown in this slide. And this code reach the code distance upper bounded by 12 and 14. And the size of the affine permutation is around 96 and 192. And those affine permutation matrices form length 32 orbits with the amount of 3 and 6. different orbits so that we can lay out the qubits on 3 by 32 2D grids. And based on the assumption of the commuting affine permutation, we also further estimate the atom shuttling schedule in a reasonable hardware assumption of the Rydberg atom array platform, so that using 4 pairs of AOD set of the experimental assumption, we can implement the atom shuttling required by the synchrony extraction circuit in the level of 10 milliseconds. And if we further allow bare pair checks or a shortcut of the atom movement, and this number can be further reduced to 2 to 4 millisecond level. After introducing how to implement this quantum error correction code on Rydberg atom hardware, I want to further talk about how this code will perform at the circuit level quantum error correction, and how we optimize the performance by introducing the hierarchical decoding strategy to produce the promising logical error rate. And to evaluate the logical error rate of certain quantum error correction codes, we need to basically need to sample many shots and decode them. And the decoding is usually the bottleneck of the whole simulation protocol, so that a faster and better decoder will usually give you more accurate assessment of the logical error rate and better logical performance. But usually the decoding is not as fast as the in the LDPC scenario. The decoding is not usually as fast as the surface code, because surface code we have the very efficient matching decoder. And nowadays there are many decoding choices in the LDPC world. So basically we have the belief propagation, which is in principle very fast, but it's not accurate enough to characterize the degeneracy of the quantum error correction code. And we also have some relay BP, which runs in polynomial time, or the BPOSD, BPLSD decoding algorithm. Both can run in polynomial time, but it's still not very accurate as the brute force decoding algorithm, such as the integer programming algorithm. A question to bring the decoding performance into practice is that we have to optimize the decoder to bring the logical error rate down and also accelerate the decoding process. One observation of the decoding is that the decoding difficulty will highly depend on the noise realization. For example, if there are not many noises or not many stabilizer are violated in the quantum error correction code, this error configuration will be easy to decode. Or basically the stabilizer, a violated stabilizer density is low, then the decoding difficulty will be much easier than the case when the decoding density or the stabilizer density is high. By taking this intuition into practice, we designed the hierarchical decoding strategy. Basically, we're taking a syndrome collected from the simulation or the experiment. We firstly pass those syndrome information into fast but not accurate decoders, such as the belief propagation decoder. And most of the shots will be captured by the belief propagation. If the belief propagation converge, then we are happy with the decoding result without running heavier decoders such as the relay BP and mixed integer programming. If the belief propagation doesn't converge, then those shots will be sent to more accurate decoders such as the relay BP. And if the relay BP converts, then we are happy. But if it doesn't converge, we will send the shot to brute force decoder, such as the mixed integer programming. But using the hierarchical structure, most of the easy shot will be handled in earlier and faster stage, and there will only be small number of the hard shots will be finally handled by the brute force decoders. So using the hierarchical decoding strategy, it significantly speed up the numerical simulation benchmarking as well as so this decoding strategy will allows us to directly sample and evaluate the logical error rate among this sample of hundreds of millions shots. By applying this decoding strategy to circuit level simulation, we benchmark the performance of the two code distance we found in our paper, where the 1000 variants and 2000 variants reach different logical error rates. So for the 2000 variants, distance upper bounded by 14, we observed one logical error in 392 million shots with 32 syndrome rounds. And the block logical error rate per round, according to this number, is around 10 to the minus 10, which already satisfies a lot of large-scale quantum error correction requirements. And the per qubit per round logical error rate is around 10 to the minus 13. So if you compare this number with the surface code logical memory, it will be significantly reduce the number of physical system requirements in terms of the physical qubit. And furthermore, we found some interesting phenomenon which already happened in the classical world. So we simulate the phenomenological error model where basically there will be two types of the error, the data qubit error and the syndrome measurement error, without simulating directly the circuit level performance. And we observe clear waterfall and error floor behavior from our simulation. So basically, the waterfall behavior will characterize the error scaling at the high physical error rate region. And in this high physical error rate region, the logical error is dominated by the high weight logical errors, where the amount of high weight logical error is significantly higher than the low weight logical errors. And because of that, the effective distance is usually greater than the minimal weight distance of the code itself. For example, in our simulation, the effective distance in the waterfall region of the P96 code and P192 code is greater than 30 and 40, and the minimum weight distance is only 12 and 14. And we also observed the error floor area. Basically, those logical error rates is dominated by the real low weight errors. And more interestingly, what we found in our simulation is that because we are using the hierarchical decoding strategy, those error floor area is dominated by the early stage decoders, including the BP and relay BP, so that the effective distance is smaller than the usual lower bound distances because the relay, sometimes the belief propagation and the relay BP converge, but it doesn't give you the correct answer to the decoding result, which means that we can further improve the performance by improving the BP and relay BP. And to summarize today's talk, we basically briefly introduce what is the recent construction by QuCS, which allows ultra-high rate quantum error correction, reaching the encoding rate using 2 physical qubits to encode 1 logical qubit on average. And from our recent paper, we also discuss how to implement this type of quantum error correction code in a hardware efficient way on neutral atom hardwares. And finally, we also discussed the more realistic performance as assessment of this type of quantum error correction code by introducing the hierarchical decoding, which gives a very promising logical error rate around 10 to the minus 10 per round and 10 to the minus 13 per round per qubit. And in future work, I would like to further explore the logical gate operation among this type of quantum error correction code. For example, further design end-to-end fault-tolerant architecture for this type of error correction code. And also another important direction I want to emphasize is to develop fast and accurate decoder. One candidate of this type of decoder, I would say, is the machine learning decoder. And recent result from Harvard also demonstrate the power of machine learning decoding on some BB code architecture. And at the end, I want to thank my collaborator from Clara, Harvard, and MIT, and also thank you for your attention. I'm happy to take any questions.